So this talk is more in the vein of what Kyle introduced on Tuesday. So more of a pattern formation, but in a more biological setting. So talking about neural field equations again, I will reintroduce those, but maybe not in so much detail because I think Kyle covered quite a lot of that already. Oh, wait. Will that work? It
should be on.
Okay. Well, it won't do the slides though, will it? So it's all right. I'll stick with this one. It's fine. Okay. So the talk falls into two parts. So first, I'm going to talk about this, these sensory-induced hallucinations. So that's where the eye is presented with some kind of image, but what you perceive is not quite exactly what you were presented with. And then in the second part, it's sort of a more general sort of idea in pattern formation, where if you're away from bifurcations, you haven't got amplitude equations, you can look at a phase for your pattern, but using some more recent techniques, using these concept of isostables, we'll see how you can get a more generalized higher order phase equations to get a more accurate picture of what's happening. Okay, so on with part one. So we're going to look at a particular class of hallucinations that you get in response to a presented image. So here is a first example where this is a stationary image, but it looks like it's moving. Some people say this one makes them feel a bit sick. I can't really see it from here. Maybe you have to see it straight on. So these snakes appear to be sort of writhing around. So you've got this hallucination of movement within a static image. The second example is we get this sort of flickering effect, so a scintillating pattern. If you look at the black dots, so that the wheel is in the periphery, again you get this sort of illusion of movement. Okay, so this is a nice one. Okay, this one also has movement, but it also has this different type of illusion where if you look at the spokes for 10 seconds-ish, if it's up there long enough, and then you look away to the blank area, people report seeing these moving but sort of orthogonal patterns. So you would see circle patterns in the sort of after image when you look away. And if you flash the spoke pattern, you see the circle image overlaid over the top. Now this does come with an epilepsy warning because it has to be flashed quite quickly. So before I get to the next bit, if you're going to be affected, then just look away. Okay, so if it makes you feel a bit sick, then I apologise for that as well. So this effect is known as the Mackay effect, where the image that you perceive is sort of orthogonal in some way to the image that you're shown. Okay, I'm going to get rid of that before anyone actually is sick. Okay, so what we want to do is describe how that sort of the movement and the orthogonal response can be described in a model of visual cortex. So how are we going to model visual cortex? So visual cortex is the back of your brain. This can be modeled as sort of a flat region. So we're going to treat it as a plane. But the mapping from what you see and the retina to what you perceive in cortex is this nonlinear mapping, which away from central vision, away from the fovea, you can take to be this, there's the pointer, this complex logarithm. So we're going to take Cartesian coordinates in cortex, and we've got polar coordinates for the retina. So this takes fan shapes become horizontal stripes, and the cortex, the circle patterns become vertical stripes. And so you can see that there's this Mackay effect is got orthogonal patterns on the retina. You also got orthogonal patterns in cortex. Okay, and obviously you have oblique lines in cortex that correspond to these sort of spiral patterns. Right, so V1 is active even without any stimulation. So this is very famous, this is very well known, that you can induce some hallucinations just by pressing down on your eyeballs or taking some drugs, which I definitely do not recommend. But people do report seeing these sort of geometric hallucinations without any visual input. So blind people also report these hallucinations in these sort of form constants of these honeycombs and lattices and spirals and tunnels. And so these can be generated in a neural field model without any external drive. So what do we mean by a neural field model? So if you remember from Kyle's talk, we have this sort of equation here where without any drive from anywhere else in the tissue, we have this exponential decay of the activity. So U here is representing some sort of average activity of the neurons at point R in your tissue at time t, and this decays without any input, but what we have is this input from this convolution, spatial convolution of the interaction kernel, which is this W function, with the firing rate function, which tells you how you process the input, the activity everyone else was seeing, into your own firing rate of the neurons at R. Okay, so little schematic here, and this is the type of interactivity function that we're going to be taking. So usually we would assume that this is the interaction between the patches of neurons at R and R prime depend just on the distance between the two populations. So we're going to take these things that look like Max and hats. So we have some areas where the interactions are excitatory, so that's where it's positive, so sort of the red-orange areas. And then we've got some areas where the interactions are inhibitory, so we've got the W is negative and blue ones. Okay, and this is our firing rate function, which we are going to take to be the sigmoid, we're not going to the limit that Kyle did with the step function. So we've got this threshold between the high response, low response, and at threshold h, the slope is mu. Okay, so we can also add some external drive to this if we wish, but if we don't, then we can still get patterns forming without that. So that's seminal work of Ehrentraut and Cowan back in 1979. They showed with us a similar setup to that. It was slightly different. I'll talk about that later. They did the linear stability analysis, and they get these doubly periodic patterns appearing. And then, so these are these doubly periodic patterns. And then if you if you put them back into the retinal coordinates, you recover a lot of these form constants of these hallucinations. Okay. So they're not all of them, but I haven't got time to talk about how you get the other ones. Right. So this is just a reminder about basically how this linear stability analysis goes. I think this will be familiar to lots of people, but just in case, it's because maybe neural field models and patterns within those may be less familiar. So we're going to assume that we've got some homogeneous steady state, and we want to see where that becomes unstable. So we first find our homogeneous steady state, and if we let our kernel be such that the areas of excitation and inhibition are equal, then we can put our steady state at 0, which is nice and convenient for all the calculations, but absolutely not necessary, but just makes everything look a bit neater. And then we do our linearization, and we get growth of wave numbers wave vectors with length k if we satisfy this dispersion relation here. So let's have a picture for what that generally looks like. The next one, here we go. Okay, so this is the Fourier transform of our connectivity kernel, and it has this single hump here, so that if we're changing the slope of our firing rate function, so that's this mu, then at some point we're going to get these things. It's going to bring that dotted line down, and at some point we're going to get the growth of some wave number. Let's call it Kc. Okay. So we get any ADIW periodic pattern with that wave number. So I've drawn some hexagons. We have all of the ones on the previous slide. Okay, so our system, without any external forcing, so this is without the forcing, it wants to form some patterns with a preferred wave number Kc, which can be calculated depending on what your exact kernel is. Right. So what am I interested in? So if you want to add external forcing to this type of system, you've got to think about how the external forcing is going to interact with the pattern that the system itself wants to make naturally. And so some psychophysicists called Bullock and Sal in around 2007 decided that they wanted to investigate this by showing a seed pattern to their participants in their experiments and flickering the background. And what they thought was that the participants would perceive that seed pattern spreading out to fill the whole of the visual field. Okay, so they showed these little fans, or they showed these little circles. So that's the black, is what they showed. And what they thought would happen was they fill out. But what really happened, what people observed, was that they filled out with these orthogonal patterns. So, like, take A, they showed this little fan in the centre of the vision, then in the periphery, we get all these hallucination of these circles. And moreover, if they were showing little circles, then they got these fan patterns, but the fan patterns rotated about 1 revolution per second, 1 revolution per second. Okay, so this was in this specific flicker rate and specific viewing distance, but this is what was perceived. So the question is, can we understand how that kind of hallucination with the orthogonal response, like the Mackay effect, occurs, and with the movement as well, just by adding some spatially periodic drive to the neural field model that we had to start with. So that's our basic model for activity in V1. So it'd be nice if we can just add a small term and get this kind of response out. Okay, so what kind of drive are we going to add? So we're going to assume that without drive, we're at the sort of a bifurcation point where we would get instability to patterns with some wave number, say Kc or K0. Sorry, it does change because of the figures there. They're the same thing. Okay, so we're going to add this forcing with some wave number Kf, and it's going to be in the form of vertical stripes across the whole domain. Okay, we'll come back to part of the domain later, but we're going to add it for tractability. We're going to add it on the whole domain. Okay, and so then we're going to multiply that by the level of activity we've already got. So we're mixing the input signal with the stateless system already, and we're just going to give it some strength. Okay, so because we're adding this forcing term, it brings into question the idea of resonance between the forcing wave number and the wave number in the x direction and the component of the wave vector of the pattern that the system naturally wants to form in the x direction. Okay, so if we were thinking about a 2-to-1 resonance, then this would be sort of the setup. We'd be interested in the resonance, the mismatch between the forcing vector kf and the x component of our already excited wave vector kf upon 2. Okay, so this distance in here, let's see if I can keep it still enough. This distance in here is this resonance mismatch. Okay, so the idea is basically that this kx is going to be kf upon 2 or kf upon n, and if we let this get really small, then this makes the y component, which has to compensate for the unfavourable kf upon 2. It has to compensate, it becomes larger, and that means we get this orthogonal response. But maybe I've given away the punchline already now, but we'll see how that occurs. So we're going to adapt for neural field models some ideas from some results of Manor and Miron, which they were looking at Swift-Hohenberg equation. Okay, so here's how the weakly nonlinear analysis goes. It's pretty standard, but you're going to expand your firing rate, and then you're going to take power series expansion for U and gamma, which is assumed to be small, so we just start with epsilon term. And then we're going to look at slow time scales, and you can also look at long space scales as well. But I'm not going to put that in the talk today. You can look it up in the paper that I'll show you later. We'll just stick to the time, changing the time scales. And we're going to assume this balanced kernel so that we can assume that our homogeneous steady state is at 0. Okay, so you do the standard thing, and you solve at first order, and you get your plane waves, and here we've got kx squared plus ky squared is k0 squared, and then solve at second order, and then at third order you get your solvability condition, which gives you your amplitude equations for the evolution of A and B, and then if you put them back into the original scaling, you get these lovely amplitude equations. So the things to note here are, don't worry about all of the coefficients and things, just the highlighted terms. So we get some terms that depend only on, so appear only when your resonance is a 2-to-1 resonance. And then you've got these other terms here, which only appear when you have anything other than a 2-to-1 resonance. Okay, you've got this little extra bit here for 1-to-1, but in general, you've got different terms for different resonances. So what we're going to do is we're going to focus on the 2-to-1 resonance. Because if you plot the Arnold tongues for these things, the one for 2-to-1 is much bigger, so you expect a richer variety of pattern forming. Okay. So this is what they look like for 2-to-1. And if you fix your kernel and your firing rate, apart from the exact slope at the threshold, then you fixed all of these coefficients that are shown in orange, which leaves you the blue ones to play around with to see what, if you change those, if you can get some nice bifurcations to these orthogonal patterns. So the remaining parameters are the distance from the bifurcation, epsilon squared delta, the forcing strength, which is gamma, and the resonance mismatch, which occurs inside phi 4, because kx and ky depend on this new resonance mismatch. Okay, how are we doing? Fine. So if we're looking for solutions in those amplitude equations now, we can find rectangles where the modulus of A is equal to the modulus of B, and we can find these oblique lines, the roll patterns, when the modulus of A is not equal to the modulus of B. And we can work out the stability and the existence of stability conditions for these patterns for various values of other parameters. So I've just picked some typical ones here. You can plot them. So the dark areas are where the pattern is stable, and the lighter areas are where it just exists. Okay, so in general, you can see that for smaller values of the forcing, the oblique patterns tend to be stable, and the rectangular patterns tend to lose stability where these stop. They tend to gain stability where they stop existing. Okay, so if you look at make some choices and take an example bifurcation diagram. So this is just a cross section at there. Nu was 0.75 k0. We fixed the distance from the bifurcation. Then we get this typical bifurcation diagram where we get this pitchfork-looking bifurcation between obliques and these rectangles. Okay, that's nice. We've got obliques and we've got rectangles, but I wanted perfectly horizontal lines. How do I get those? So if we can make a plan form, plan forms for each of the stable patterns for a variety of parameter values. So here we have the forcing strength. As we increase that, we go from the obliques to the rectangles. But as we change nu, going towards k0, so that's the resonance mismatch going right, making right quite big and taking our wave vector to have a very large ky component, we get these horizontal response. Okay, so this is nice. So we might be able to explain how in these, if we force with vertical stripes, our output is horizontal stripes, so long as we've taken this resonance mismatch between our forcing wave number and the natural pattern to be sufficiently to have the right kind of relationship. Right, okay. But also we wanted the pattern that we get out to be moving. So it turns out that if I went all the way back, but I won't, the dispersion relation that we had for the original model only allowed for real eigenvalues. So what we want is a dynamic instability. So we need to add a little bit more to our model. So you could do that by having this two population model that of Ehrentraut and Cowan. So you have an excitatory and an inhibitory population at every point in your cortex, in your domain. But what we're going to do is instead we're going to consider a different sort of two-dimensional problem where you've added some feedback, so some adaptation. So you can solve this equation here for A because it's linear, and what we can do is we can make this back into one equation. This is why we prefer this way, because we can just deal with one equation which now has this time convolution in it, which comes from solving that linear equation from A and putting the result back in here. Okay, important quantity is going to be the Laplace transform of this eta is going to appear in our new amplitude equations. So I'll just put it up what it is. Right. So we repeat everything, right? We find our new dispersion relation, which now has this eta of lambda over here, and so now we can get complex eigenvalues, and so that we can find this Turing-Hopf bifurcation. It occurs for some and excites some wave numbers k0, and we find this emergent frequency of the oscillatory pattern that we get out. Okay, and now if we wanted to continue in two spatial dimensions as well, everything's going to get a bit complicated because what we're going to have is 4 complex amplitudes. So you're going to have four complex amplitude equations, and that's a bit hard to analyze. So what we do is we're only looking to demonstrate that we can get this movement out. We're going to skip down, reduce down, and just look at one spatial dimension. Okay, so just hope we get the movement out there. Okay, so now we just get rid of a couple of the amplitudes, and we're just interested in one dimension. Oh, that's not right. There we go. Okay, so here are our amplitude equations. Get the right button. Amplitude equations for one spatial dimension for A and B. Okay, so now this lambda here depends on higher order derivatives of our spatial kernel. But okay, this is what they look like, basically the same, but we've added in this extra bit to our linear component here. But the upshot is, if I can get to the next slide, there we go. Oh, it's gone too far. I think my computer's not very happy. And now I'm giving away what happens later. Right, here we go. Okay, so we get these travelling wave solutions for small values of the forcing strength, and then these become unstable to these sort of standing wave solutions as you go further away. Okay, so the travelling waves would correspond to these rotating patterns, and standing waves would be sort of like scintillating patterns. Okay, so we get what we wanted for sort of smaller values of the forcing. Okay, so we can get movement, and we can get this orthogonal response, but what we've done is we've put the forcing only on, we put it everywhere to do the analysis, but the experiments with Billick and Sau, they just showed a seed pattern on part of the domain. So what happens if we try and reproduce that? So we're going to do some numerical simulations, and we're going to put, only going to give the seed pattern on part of the domain. Then it turns out that it doesn't really matter because we still get the same sort of response. So here we've got the direct correspondence. So these are for numerical simulations of the equations without adaptation, so we don't expect any movement here. But it does mean that I can nicely transform what we get from cortex back So the retinal coordinates was easier to directly compare, and yes, we can get all of the nice patterns out. Yeah, including the sort of right numbers of spokes and circles and things, which is very nice. Right, but if we want to add in the movement as well, then we're going to need to use this model with the adaptation. And when we do that, you can see these are the numerical simulations should be running. The ones that don't have the movement, so the A and C, are not changing basically. But you get these orthogonal patterns on the two parts of the domain, and these eventually will settle down to have roughly, or at least locally, orthogonal patterns. So the left, so I should have said the left half of the square domain is the central vision, and the right half is the periphery. Okay, so are they going to settle down? Yes, okay. They take quite a long time. Okay, so now we've roughly got these horizontal patterns moving there. Okay. Right, let's move on to the next one. So the eagle-eyed among you might have noticed that I didn't have any flicker in my simulations, which is what Villock and Sau had in their experiments in the background, so a background empty flicker. But we found that we didn't really need that to get the results. So we postulate that's because they needed the background flicker to bring cortex to the point where it would naturally form those spontaneous. So you'd be allowed to see the spontaneous activity in V1. So yeah, and we've done that using just tuning our model parameters to get that to that point. But if you did want to add some flicker to your numerical experiments, then it doesn't change its thing. It has no effect at all, and no discernible effect. Right, so conclusions of part 1, just about on time, are that the psychophysical experiments that Villock and Sau did with showing this orthogonal response can be explained with a very simple neural field model with a 2-to-1 resonance between the spatial forcing and the natural pattern that the system wants to form. And if we add some negative feedback, then we can get the movement as well, which corresponds to the rotating percepts. And then the direct numerical experiments showed that you can get the same results when the patterns are presented only on the half space. Right, okay, and there's a paper a couple of years ago now on that. Right, how might we extend it? So if you think about more structured, complex inputs, so this is the Enigma hallucination, if you like, by Leviant. So it's a famous piece of artwork where people observe sort of movement within the grey channels. So this is a fairly simple geometric pattern, might be easy to put that into a neural field model and see what we get out. Or you can think about completion illusions, so where you show a pattern where there's a blank section in the middle, and then you wonder how cortex will fill in that pattern. So sort of it's likely to depend on how big your blank area is and sort of the orientation of the pattern that's around it. So I had a MSc student who did a little bit of work on that. Or you might want to add spatiotemporal drive. That's a bit more complicated. Right. I think that is all on part 1. So let's just move on to part 2, which is a little bit different. So we were able to get amplitude equations near to a bifurcation, but if you're further away from a bifurcation and you've got an oscillatory pattern, how do you describe how that pattern evolves? So the classical technique would be to say, right, everywhere in my tissue is oscillating, and so I can describe a phase. Okay, so it's got a very general sort of form of model. We've got some U that we're interested in, which might be neural activity. Could be some flow, if you like. Okay, and we've got F is some nonlinear operator, and this describes what's happening locally. And then we've got some external input or interactions with other parts of your domain, described by G. Okay, so we're going to assume that U has got some stable periodic orbit at all points. Okay, we're going to call that Y, and the period is going to be T. Then we can define this phase on this limit cycle Y everywhere. Okay, because if you're on the cycle, then it's obvious how you do that. If you're off cycle, then you define the phase asymptotically. So if you start off cycle, then you get attracted to cycle, and the asymptotic phase is basically where the point on cycle where you get back onto the cycle. So this is little animation is probably describing that better than I am. So the red dots originally will start out distance away from the limit cycle of the one that's on there, and eventually they all join up, which means that they all have the same asymptotic phase. So this blue line here is an example of an isochron. So points on the same isochron have the same asymptotic phase. And that asymptotic phase it evolves without any input. So when epsilon is 0, if you like, the phase just is constantly increasing. Okay, right, and then in response to perturbations, you have to give some idea of how the system, how the phase responds to perturbations, and that's given by this phase response function, okay, which I'm going to call Z. So does the perturbation advance or retard the phase? This is sort of quantified by the Z, which is the gradient of the phase function, the function that assigns a phase to each point in your phase space. And that function, that phase response function, can be computed. You're just solving this adjoint equation. It's just a first order ODE, except this thing here depends on beta itself. Okay, so we can numerically solve that. We've got some normalization condition, and then so we're just going to then we have our nice equation for the evolution of the phase. And if we just write what our G is in terms of theta and phi, then we can write, if we assume that we're staying on the cycle, then we can find an equation for beta. Okay, so all of this assumes that the perturbations are small, so we never move far from the limit cycle. So we can assume that we evaluate the phase response only on cycle, and basically U always stays on the limit cycle. Right. So if we were to pick a neural system for our U up here, how would this look like? Okay, so the example I'm going to be thinking about is this Wilson-Cowan model, okay? So the continuum Wilson-Cowan model. So this is another example of a neural field model, except now everywhere in cortex we have at different positions X and Y. Everywhere we have inhibitory population and an excitatory population, and these are interacting by these interactions here, which I put zeros on to mean that they are local. They're all occurring at point X. And then, so that would be your F. Your F system is everything that's happening here, and then your G is everything that's coming from a different point in cortex Y, which comes from these convolutions here. Okay, so these convolutions excluding what's happening at X. Okay, so we're going to separate out our kernel from the local bit at X equals 0, which is going to be some constant, and then we've got everywhere else is this sort of a Mexican hat shape. Okay, but now they're all positive everywhere, and so we've got these coefficients that tell us whether we're excitatory or inhibitory connections. Okay, so these W alpha betas are telling you the input to alpha from beta. Okay, so an alpha beta is either E or I, depending on whether you've got excitatory population or the inhibitory population. Right. So keeping the same sort of form of firing rate, and I think we'll move on. So this is just all in 1D now. So we're just thinking about patterns on a line. Right, so the next thing you would go to is compute your phase response curve, and that happens to look something like this for that particular model for some choices of kernel and firing rate. It doesn't really matter, they're sort of wiggly. And then R with G for that particular model, this form. But the main point is that you've got this order epsilon correction term to the constantly increasing theta. Okay, and we can write out what that is in terms of things that we can calculate. Okay, so we've got this function that describes the evolution of theta, and if we average it, we get an even nicer equation because now we've got this phase difference part here, and we've got this interaction function h1, which we can calculate once we've got the phase response and we know what the limit cycle is. Okay, so that's nice. This is our generalized phase equation, which is good, but it's only valid where epsilon is very small because we need to stay basically on, it needs to be a good enough approximation that we stay on the limit cycle. However, in many cases, we're not always going to be on the limit cycle. Our perturbations might be larger, taking us away from the limit cycle, or we might have slow decay to the limit cycle in one direction. So what do we do in that case? We might not expect this first order approximation for the phase equation to be very accurate. So what we can do is we can introduce this idea of isostables, which give us a coordinate, it's sort of a proxy for distance from the limit cycle. Okay, so these isostable coordinates, which are called psi, you've got one of those in each direction of each of your Floquet directions. Okay, so we've got decay in those directions related to the Floquet, for the corresponding Floquet exponent. Okay, so we've got this exponential decay because we're assuming that the limit cycle is stable. So all of these kappas, we're going to assume that they're real. You can do something corresponding. It's not too tricky to make them complex, but it's easier to picture them being real for now. Okay, so we've got this decay to the limit cycle. So on the limit cycle, your isostable coordinate is 0, and then we've got this relaxation time to cycle in each direction. If we only track one direction, so we said that there's some type of separation of the relaxation rates, so that one is not noticeably slower than the others, and we just keep that one and say that everything else does actually collapse back to the limit cycle infinitely fast, so we can just disregard those. We just keep the one. Then we can have sort of this picture in our head. We've got our limit cycle, and all of these red dots, starting on each of these other, they're circles in this picture, but they would just be somewhere around the limit cycle. They all decay back to the limit cycle at the same rate. So they're passing each of these level sets of these isostable coordinates at the same time, and they get back to limit cycle at the same time. Okay, so these dotted blue lines would be called the isostables. Right. So we also need to have a response for these isostable coordinates, so we can calculate what that is as well. The isostable response, basically, if you make a perturbation, do you get back to limit cycle faster, or does it take you longer? And it's the gradient of the definition of what your isostable coordinate is. I appreciate that I've not written that down because we don't need it, because if you're staying fairly near to the limit cycle, then you can evaluate that on cycle. You evaluate you only need the value of the isostable response on cycle. Okay, so that's this I thing here, and now we can use that to describe what's happening off cycle. So U is now allowed to be on cycle plus a bit off cycle in the direction of our Floquet eigenvectors by the amount of the isostable coordinate. And similarly, we can rewrite our Z, so our phase response function, as the bit on cycle plus a bit off cycle. Okay, related to this, so it's like expanding in the isostable coordinates. So this B is just like a higher order correction to your phase response. Okay, and these, I haven't written them down, but these flock A eigendirections and this B, they can also be evaluated by solving some first order differential equation, sort of an adjoint equation for B, and something similar to the limit cycle for the rows. Okay, so now if you were to do this for Wilson-Cowan, then your G function wouldn't have any external, you're not having any external input. The input is just from all the other points in tissue. And so you can expand your G by just a Taylor series in two variables, and you get something like this. So this is what we would have normally, and then, sorry, I say normally, for first order phase expansion, and for second order, we now have this isostable coordinate coming in here. And we're going to assume that that is order epsilon. Okay, so we're staying reasonably close to limit cycle, but we are able to move off a little bit. Okay, so that means that we got, if we just go to order epsilon, so we don't need this term here, we're making an order epsilon expansion here, because we're going to throw those away, because then what we're left with is a first order differential equation for psi, which we can solve. Hooray. And we can write down exactly what psi is, and then that means that when we write down the phase equation, which is going to have this term in it, we can substitute this psi into there, and we get an updated phase equation. Okay, where are you going to go? Yay, okay. Updated phase equation. So this is what we had before, just the first order terms, and now we've got these second order terms which come from the second order terms in G. Okay, so we've got this the original phase response and the higher order terms from the interactions, and then we've also got the higher order term in the phase response and this first order term from the interactions. Okay, giving us our order epsilon terms, which means that, okay, for Wilson-Cowan, if you care, you can write them out. The main point is that everything in here can be calculated by solving a first order differential equation. Okay, numerically, but still, it's pretty straightforward to do so. So you can find all of these interaction functions in a pretty straightforward way, okay? These doubly periodic things. So if you wanted to do something clever with Fourier series, you'd have to do a double Fourier series thing, but it's all doable. Okay, which means you get this nice, if you want to look at patterns in the system, you can look at simple patterns and see where they become unstable. So we were thinking about, I've got very little time left, okay, but I'm right at the end. We've got these phase wave solutions we can find within the equations, and we're looking at their linear stability. Then we write down our updated dispersion relations to the orange terms are the extra ones that we get from having higher order terms, and these basically look like this. If you look like this, they look a bit like this, then that means that for this particular value of eta, so that the wave number of the pattern, and epsilon, so the strength of the interactions, this means that this particular pattern is unstable, because we've got the real part of lambda is positive in some region. Okay, so we can just repeat that over the epsilon eta plane, and the point is that when you have these higher order terms, we can get something more interesting than just this straight line boundary between where these phase waves are stable and where they become unstable. Okay, because we've got higher order terms, this boundary becomes more interesting, and so we can say what happens for stronger interactions is not the same as what happens when we're just looking at the sort of weak limit down here. So we've got agreement here, but then the boundary is actually more interesting, and this is telling us that here, for example, we'd actually see more interesting patterns than these phase waves, whereas if we'd use this approximation, we'd expect stable phase waves. Okay, so finally, because this is the thing about, there's lots of people talking about turbulence, if you make particular choices about your kernel, and then you can write out what this convolution is as an approximation using different partial derivatives of theta, and you make further choices, which I won't go into exactly what they have to be, you can get down to a phase equation that looks like a Kuramoto-Shib efficiency equation, and that has weak phase turbulence. So I've got turbulence in there somewhere. Okay, and this is a gratuitous simulation of the Kuramoto-Shib efficiency equation. Okay, so what we'd like to do is we'd like to go beyond the Wilson-Cowan equations and look at your next generation neural field models. We'd like to include some delays, and we'd like to look at 2D patterns. So what we'd really like to do is try and explain some chimera-like behaviour that we've seen in some simulations of these next generation neural field models. And I won't go into exactly what they are, but if you talk to me or Kyle, we can give you some more information about that. Okay, so that's everything. This is my acknowledgements for people I've worked with, and paper. Thank you.
Thank you very much. Any questions?
I have a very, very quick one. So in the last bit where you were talking about the changes in these stability regions you get by including these higher order terms, sort of very simple and obvious question is, well, how does that compare to if you just simulate the full system?
Yes, that is what we would like to do, but now you're forcing me to admit. This is very recent work, and in making this, I discovered problems in the PhD student's work, and he will be, yes, definitely on it to do the simulations to compare this with the simulations of the full thing. It just hasn't happened yet, due to noticing a few problems that needed ironing out first. Yes.
People report hallucinations when they're deprived of stimulation, like in a dark room for a long period of time. Could that be included in your model by adding some stochastic forcing?
I guess so, and I guess that it sort of comes under the spontaneous pattern formation bit, where you don't actually see all these hallucinations all the time. So there's some stochasticity that's preventing you from seeing these random geometric hallucinations all the time. So I guess if you're deprived of external input, then perhaps those come to the fore. Yeah, but obviously then you don't have all this external drive patterns coming in. But yeah, I guess.
I have a question, and it's sort of from my personal experience. So I have visual migraine. So when you showed the flickering images, I had to look away.
Yeah.
And I'm kind of interested in like how robust is this to variations in different people's brains? Because as somebody who suffers from visual migraine, I know that there are some times when I'm in a kind of pre-migrainous state, and I'll be more likely to have a migraine, and maybe quite frequently. But there still needs to be often some kind of stimulus, and there needs to be quite a specific stimulus. And I'm just kind of, I mean, I guess that's spontaneous pattern formation in a way, but the stimulus is transitory and it has to be of a particular kind.
I don't know, this is a very interesting question, and people have looked at get these aura patterns as well.
Yeah, that's exactly what the visual migraine is.
Yeah, yes, so they get these sort of like half moon shapes, so they're generally reported. Yes, I do know about people who've worked in that area, but I don't really know how it's related to these hallucination.
I mean, I think they're really similar. The patterns are really similar, I can tell you.
Okay.
And they would be interesting. And they go out in circles.
Wow. Okay.
Yeah.
It's really interesting.
Yeah, it's not very nice.
No. I can see it's not very nice.
Very, very quickly. Experimentally, you get U or F over U. You have the F function, right, acting on U, which is the sigmoid function which circulates it.
Yes.
But experimentally, what you are observing is the U or the FU.
Well, U. But I mean, these models are completely phenomenological. So it's just a hypothesis of what that F should look like. If you look at these next generation models, they are derived from some kind of spiking network. And you can derive what that F has to be, and it is not that. It's completely different.
A lot of your results are universal with respect to some general form of F. Something that saturates.
Yeah, it just has to be something that saturates, and we just pick something. Yeah, it just has to be that kind of shape for this to work.
Okay, thank you again.